Now that we've talked about parallelograms, let's talk about a few special parallelograms. So it's going to be 6-4, properties of special parallelograms. And just a quick math fact, the fewest number of colors needed to color any map so that no two adjacent countries, two countries next to each other, so that no two countries next to each other share a color is 4. So if ever you're coloring a map and you want to make it so that you don't have two countries next to each other, all you need is 4 different colors to do this. We have 3 types of special parallelograms. You've probably heard these terms before, but the first is a square, then a rectangle, and a rhombus. This does go in the opposite order of your book, but I like doing this order because everything can be made from a square. Of course you know what a square is, but for a formal definition, it is a quadrilateral with 4 right angles and 4 congruent sides. So of course you know what one looks like, but we have a square as such, and we can call this square A, B, C, D. Now we know it's a square because we have all sides congruent, and the part that most people forget about is that we have 4 right angles. And then we also have a term called a rectangle, and of course you know what a rectangle is, but it is a quadrilateral with 4 right angles. Now notice I kept my square ABCD drawn here. The reason why I did this is because a rectangle is very similar to a square with one slight change. Is that we can start from A and go all the way down, but all I'm going to do is I'm going to extend a side. It's almost as if I put my fingers on either end of this square and I just stretched it out. And what that has given me is now rectangle ABCD. And it is traced in blue. And we still have a right angle, and all I did was stretch it out, so we still have our right angles here. The difference here between a square and a rectangle is that now not all 4 sides are congruent, which is important to know. Now let's go ahead and talk about 2 theorems dealing with rectangles. The first, theorem 6-4-1, says if a quadrilateral is a rectangle, then it is a parallelogram. In other words, all rectangles are parallelograms. So if you have a rectangle, we know it's a rectangle because of the 4 right angles, and we can call it, again, rectangle ABCD. So if we have this rectangle, because of this theorem, we instantly know that ABCD is a parallelogram. Now it is important to know that this theorem does not work the other way, meaning all parallelograms are not rectangles, but all rectangles are parallelograms. And something you must remember, since all rectangles are parallelograms, all of those theorems from 6-2 that we talked about, the ones that dealt with parallelograms, they are also true for rectangles. So meaning the opposite sides are, or the opposite angles are congruent, the opposite sides are congruent, adjacent angles are supplementary, and that the diagonals will bisect each other. All of those theorems are true for rectangles. Our second theorem says that if a parallelogram is a rectangle, then its diagonals are congruent. In other words, rectangles have congruent diagonals. So I have a shape here, ABCD, and I know it's a rectangle because I have 4 right angles. So if I drew in my diagonals, if I drew in BD and AC, what this theorem tells us is that AC is congruent to BD. And this is because it is a rectangle. This is because we had these right angles, the 4 right angles. So looking at an example dealing with rectangles, it says that rectangle RSTV has RS is equal to 50 and the length of RT is 86. Find the length of OV. So I'm just going to go ahead and go around my picture. And again, we know this is a rectangle because we have 4 right angles. So I'm going to go along my diagram though and label this RS is equal to 50 and RT is equal to 86. And I want to find OV. So I want to find the length from O to V. Alright, well, what I'm thinking is, right now we can't do this. Right now we can't determine what OV is based upon the 50 or the 86. Notice how OV is part of the other diagonal, it's part of SV. So if we try to relate the two diagonals, if we try to relate SV and RT, well, luckily we have a theorem that does that. Theorem 6-4-2, that one that we just talked about, we can say that SV is congruent to RT. Alright, well that's helpful. The diagonals are congruent. What that means is that SV is also 86. Both diagonals are 86. Now, thinking about a diagonal, we still need to know this bottom of the diagonal. Remember at the beginning when I introduced rectangles? It is also a parallelogram. So let's say from 6-2, remember that all diagonals bisect each other? So since diagonals bisect each other, we know that diagonal SV was cut in half. Means that OV is congruent to SO. Or if we wanted to find OV, all we would have to do is take the total length and divide it by 2. We need to take 86 divided by 2, which gives you 43. And what that means is that both of these lengths are 43 because SV is bisected. So notice that we used our new theorems and 6-2 stuff. Don't forget about 6-2. Now we're going to go ahead and leave rectangles, but we're going to start with a square again. We're going to come up with a new shape, but it all starts with a square. Remember, a square has 4 right angles and 4 congruent sides. Now imagine that we had a man pushing this top of this square. Now what would happen to this square is that it's going to end up, the top is going to be pushed over. And we still have those sides congruent. The side lengths didn't change at all. All what was happened was it was pushed over. But notice that these angles are not 90 degrees. None of these angles are right angles. So that's the big difference between a square and this new shape, is that all of the side lengths are still congruent. The side lengths didn't change at all, but you no longer have those right angles. What we call this shape is a rhombus. And a rhombus has a definition easy enough. It is a quadrilateral with 4 congruent sides. Now we're going to talk about 3 theorems dealing with rhombuses. The first one, theorem 6-3-4, says if a quadrilateral is a rhombus, then it is a parallelogram. In other words, all rhombuses are parallelograms. So if we had a rhombus as such, and we can call it again A, B, C, D, and the reason why we know this is a rhombus is because all sides are congruent. What we can instantly say is that A, B, C, D is a parallelogram. And just like rectangles, make sure you realize that since all rhombuses are parallelograms, all of the theorems from 6-2 about the parallelograms are also true for rhombuses. Our next theorem, theorem 6-4-4, says if a parallelogram is a rhombus, then its diagonals are perpendicular. In other words, rhombuses have perpendicular diagonals. So what that means is if I drew our diagonals, if I drew AC and BD, these two diagonal lines, AC and DB, these two segments are perpendicular, meaning that we have right angles in here. Those lines form 90-degree angles due to it being a rhombus. And finally, our last theorem says that if a parallelogram is a rhombus, then each diagonal bisects a pair of opposite angles. Or in other words, rhombuses have diagonals that bisect opposite angles. So I drew our rhombus ABCD, and again, we know it's a rhombus because we have 4 congruent sides. And I also drew our diagonals BD and AC. What this theorem tells us is that each diagonal, so let's talk about AC. AC bisects angle A and angle C. So angle 1 and 2 are congruent. Also, angle 6 and angle 5 are congruent. But then now if we talk about BD, angle 3 is congruent to angle 4, and angle 8 is congruent to angle 7. So let's look at an example dealing with rhombuses. It says that CDFG is a rhombus, and we want to first find the length of CD, and then part B says to find the measurement of angle GCH if the measurement of angle GCD is equal to B plus 3, and the measurement of angle CDF is equal to 6B minus 40. Starting with part A though. Part A, we want to find the length of CD. Well, first and foremost, the directions say that this is a rhombus. So we can go ahead and mark our rhombus as having congruent sides. We could say then that CD is congruent to CG and also congruent to GF. Why is this important? Because we could find the length of both of these measurements. If these two are congruent, which they are, it's a rhombus, we could say that 5A is equal to 3A plus 17. Solving for A, we subtract 3A, subtract 3A. 2A is equal to 17, and thus A is equal to, oops, I divided by A. I wanted to divide by 2 there. Thus A is equal to 17 over 2. Now that we have A, remember that our directions are not to find A, our directions are to find CD. Well, we don't have anything talking about A for CD, but we do know that CD is congruent to all the sides. So all we now have to do is find the length of a side. We know that CG is equal to 5 times 17 over 2. And if you multiply this out, you get 42.5. What this means is that every single length is 42.5, and therefore our answer is 42.5. Okay, now looking at part B, we want to find angle measurements now. So we are told that GCD is equal to B plus 3. So this entire angle is B plus 3. And the measurement of CDF, so CDF, this angle up here, the top angle, is 6B minus 40. And what we want to find is we want to find the measurement of GCH. So we just want to find this smaller angle. Well, one thing that we do know is that a rhombus is a parallelogram. So we could use our stuff from 6-2, and we could say that B plus 3 plus 6b minus 40 is equal to 180 degrees. We had a theorem that said that. We had a theorem that said these two consecutive angles are supplementary. They add to 180. So let's solve for b now. We have 7b minus 37 is equal to 180. 7b is equal to 217. And we see that b is equal to 31. Well, that's nice, but now we need to actually find out what the angle is. Since b is 31, we can take this 31 and plug it in for b over here. This will tell us that the measurement of angle GCD is equal to 31 plus 3, or in other words, 34 degrees. Now we also have a theorem that says, and this is the new theorem, says that this diagonal in a rhombus will bisect angles. So we can say that from our theorem that says that diagonals bisect angles, we know that this little green mark, the green section that I marked, is going to be exactly half of that angle C, of that angle GCD. It's exactly half of it. So therefore, the measurement of angle GCH, what we're looking for, is equal to 34 divided by 2, or in other words, 17 degrees. I know that this one is a little bit trickier, but just remember that it is a parallelogram still, and we have all these new theorems dealing with rhombuses.